All right, so we're going to be talking about what ionization energy is and data that pertains to ionization energy. So ionization energy is basically the energy required to remove one electron. But the actual definition, if you go look it up, is going to say it's the minimum energy required to remove one electron from an atom in its gaseous state. So that verbiage is important here because they might ask you to write an equation, so you have to indicate that it's in the gaseous state to do that. So if we take some metal in the gaseous state and then we apply energy to it and we apply the minimum amount, we are going to eject an electron, so we're going to move that electron, and then we're going to be left with the positive ion. So remember, if you remove an electron, you're going to get a positively charged ion. So this is the first ionization energy. So that's the energy it takes to remove the first electron. Now let's say that I want to remove 2 electrons. Well, I have to remove the first one first, and then I can go and take the positive ion that I created in that first step, apply more energy to it, and then get a more positively charged ion with another electron. So this is the second ionization energy. So remember, that's the energy to remove the next electron. Then I can keep going, and I can keep doing this with all of the available electrons. So if I were to take the same ion that I just created, apply even more energy to it, I can eject a new electron, or the next one. Now, the thing is, every time you apply energy, that amount of energy goes up. So maybe it takes 50 kilojoules to remove the first one. Then the next one it takes, I don't know, 150 kilojoules. And then the next one, maybe it requires 500 kilojoules. So every time that you remove an electron, it requires more and more energy. And the reason that that is because the number of protons is staying the same. Well, every time you take off an electron, you're removing one of the repulsions that the next electron would feel. So those electrons are now filling the pull of the nucleus even more. So they're more attracted to the nucleus. So it's going to take more and more energy to remove those electrons the closer and closer we get to the nucleus and the more electrons that we remove. All right, so right here, this shows us the first ionization energy for the first 20 elements. So remember, the first ionization energy is going to be the energy to remove the first electron. So we look at it, well, it goes from hydrogen to helium, it goes up, and then we go from lithium to neon, it's going up, and it goes back down, and then it goes from sodium to argon, and it's going up in general. So when we look and we're talking about going down a group, well, okay, if we have helium, well, if I'm looking at the noble gases, helium is followed by neon, which is then followed by argon. So down a group would be these 3 elements. And I see that the trend is that the ionization energy is going down. It takes less energy to remove the first electron. Then I'm looking at this trend, where I go from lithium to neon. Well, if I look at where those are on the periodic table, lithium to neon would be the second row of the periodic table. So across the period, it's going up. So as I go across the period, the trend is that the ionization energy gets higher. It takes more energy to remove that first electron. Well, why is that happening? Why does it take more and more energy as I go across the period? Well, as I'm going across the period, what else is increasing? The number of protons. The number of protons increases. And remember, we don't have extra shielding because we haven't gone to the next energy level yet. So the number of protons is increasing, so the effective nuclear charge is higher, which means the electrons are more attracted to that nucleus. So as I go up a group, the ionization energy will go higher. So in the data we saw, it was going down the group, so it was getting lower. Same difference. The reason that that happens is because we're moving further away from the nucleus. So as I go down a group, the number of protons will increase, but the shielding is also increasing, and that counteracts the effective nuclear charge. So even though I'm increasing my number of protons, my electrons are getting put on outer energy levels, which means there's more shielding. So remember, shielding is when those core electrons are repelling the valence electrons away from the nucleus. So remember, core electrons are on the inner energy levels, valence electrons are on the outside energy level, and if you have more and more core electrons on your inner energy levels, the electrons on the valence shell are not going to feel the pull of the nucleus as strongly. So, what does all of the data show us? So if we were to go and gather the ionization energy for all of the elements, what does it show us? It shows us there's a repeating pattern. So as we go down the group, we're going to see a decrease in ionization energy. As I go across the period, we're going to see an increase. But we also, if we look at all of the data, we can see that the alkali metals have the lowest ionization energy. Well, all the alkali metals, the configuration will be S1 and on the outer energy level. So there's one electron on that outside energy level. It doesn't take as much energy to remove that. Noble gases will have the highest, and that's because its S and P sublevel are full on the outside energy level. And then you see that the pattern starts to repeat after 2, then 8, then 18. Well, there's 2 electrons on the first energy level, there's 8 electrons on the second, there's 18 electrons on the third. So this shows how many electrons can fit onto each energy level and also each sublevel. And I'll show you a little bit more of that in a second. Now, it's easier to remove an electron from a new sublevel versus a full sublevel. So if we go from, let's see, if we have 1s, or let's do 2s, 2s2, and then 2p1 versus 2s2, 2p6, it's actually a little bit easier to remove this electron because it's on another sublevel. And it also provides evidence for Hund's rule, where you have to fill empty orbitals before you start to pair them. So let's look at some more data that kind of shows some of this. So let's look at the ionization energies for potassium. So these are the successive ionization energies. So it means I've removed the first electron, then I've removed the second, and then the third, and so on. So when I look at this, in general, the pattern is that ionization energy is increasing. But you'll see right here and right here, I have pretty large jumps compared to the jump from here to here or here to here. So what's happening? Well, let's look at the configuration. So if we look at potassium's configuration, it is 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1. So if I'm looking at these configurations right here, if I'm looking at this one, well, after the first electron, so I removed this one, now I'm on a lower energy level. So these electrons are going to be closer to the nucleus, and also I've removed that extra repulsion. So it gets a little bit harder to remove the next electron. Well, then I remove, let's see, 1, 2, 3, 4, 5, 6 electrons. So there's 6 electrons that I've removed. And then I have another jump going to the 7th electron. Well, if I remove 6 electrons, that's that. And then right here, if I try to remove the next one, well, now I've changed my sublevel. So now if I'm looking at this sublevel going into the 3s, well, the 3s is going to be a little bit closer to the nucleus. It's going to be a little bit harder to remove that. So it'd be easier to remove the electrons from the p sublevel first. So again, we saw 2 large jumps in between the first and the second, and the 7th and the 8th, and that's because it takes more energy to remove those electrons. So after you remove the first, then you have to remove an electron from the next energy level in. After you remove the 7th, you have to remove an electron from another sublevel, which happens to be the s, which is a little bit closer to our nucleus. All right, so now let's look at some other pieces of data. So this is the same chart that we were just looking at, but if we look, aluminum and boron are a little bit different. Here's boron, here's aluminum. So when I look at this, the trend is that the ionization energy is going up, but boron actually goes down from beryllium. So if I look at the periodic table, beryllium is more towards the left, and then we go to boron. Boron should be a little bit higher, but it's not true, and that's the same thing for aluminum. Well, the reason that we have a discrepancy here lies with the configuration. So whenever we're looking at discrepancies in data for ionization energy, always look at the configurations. So our configuration for boron, 1s2, 2s2, 2p1. The next one is boron or aluminum, 1s2, 2s2, 2p6, 3s2, 3p1. Well, if we look at that right there, we have an electron and the p sublevel. So this is telling us that it takes a little bit less energy to remove that next electron because it's in the p sublevel, which is a little bit further away from the nucleus. So it actually decreases a little bit from beryllium. So again, if we're looking at any kind of discrepancy with ionization energy, always look at your configuration because the answer is there. All right, so let's look at the other one. The other configuration that's, or discrepancy, is with sulfur and oxygen, which is here and here. So from phosphorus to sulfur, it decreases instead of increases. Same thing here. Well, let's look at our configuration. So for oxygen, 1s2, 2s2, 2p, 2p, let's see, 4. Well, when I look at this, well, 2p4, if I look at the orbital diagram, it looks like this. One electron up, one electron up, one electron up. The next one goes down. Well, if I'm going to go and remove an electron here, I'm going to remove this one. Why would it be a little bit easier to remove it? Well, look at what's happening right there. You've got a pairing. You've got an electron-electron pairing. And remember, electrons repel each other. So it's a little bit easier to remove that because of that repulsion there. And the same thing is true for sulfur. Sulfur's configuration also ends with p4. So it's a little bit easier to remove that electron because of the repulsion there. Now, it's not going to be true for the next electron. So if I were to have 5, because I actually have an extra proton at that point. So that extra proton will actually counteract any kind of repulsion that you have in the next orbital. So just remember, anytime that they say that there's a discrepancy, why is there a discrepancy? It always lies in the electron configuration. All right, so how else can they present data to you? Well, it can look like this. It can look like numbers. So when you're looking at data like this, it goes from 700 to 1400 to 7000 and so on. Well, when you look at this, you need to look for the large jumps because that's going to indicate something to us. So it goes from 700 to 1400, so doubles, okay. And then it goes to 7000. Then it goes to 10,000, so it goes up by 3. Then it goes up by 3 again. It goes up about 5. Well, if I'm looking at this, well, if I look at all the rest of the data here, this is a rather large jump from 1400 to 7000. So that indicates that it's a little bit harder to remove the third electron. Well, it's going to be harder to remove an electron if it's on an inside energy level. This indicates that this atom or element only has 2 valence electrons. It only has 2 valence electrons, which means it's in what group? It should be group 2. So it's in group 2. We're going to remove those 2 electrons. The next electron that I would need to remove would be on an inner energy level, which makes it harder, which means that there's going to be a huge jump between those electrons. So those jumps, we're looking for the largest jumps. those jumps are going to indicate that we've moved into an inside energy level. If we're looking at the 12th electron, though, really the only thing that we can say is that it's the closest one to the nucleus from the data that we have seen here. And if we want to identify the group that the element is, well, it's in group 2 because it has 2 valence electrons. So when we're looking at data like this, we're looking for that first large jump, and that's going to tell us how many valence electrons we had. So if we went from, like, let's say 50 to 100, and it won't be quite like this clean, to maybe 150, and then all of a sudden it jumps up to 600. Well, if I'm looking at that, that jump happens here. So it's easy to remove the first 3 and then hard to remove the next one. So that means it has 3 valence electrons. It has to be in group 3. And of course it won't look this clean, but that's just another example of it.